What if a galaxy existed, glowing with stars, swirling with gas, dust, and planets, and was completely missing the one ingredient that every single galaxy is supposed to be made of? And what if we only just confirmed one of these impossible objects, sitting in a perfect straight line with two others that have already been picking fights with everything we thought we knew about how the universe is built? Before we go any deeper, hit subscribe and tap that like icon right now, because this discovery is tied directly to the woman whose name now sits on the most powerful sky mapping machine ever built. And what we're about to walk through will change the way you picture what a galaxy really is. Now stay with me, because the strangeness of this moment does not come from the object itself. It comes from what the object is missing. When astronomers look out into the universe and study galaxies, they almost always find the same invisible scaffolding holding them together. Something they cannot see. Something that gives off no light, reflects no radiation, and refuses to show itself to any telescope humans have ever built. That something is called dark matter, and for decades it has been the quiet background character in the story of nearly every galaxy anyone has ever studied, the silent author of every chapter we thought we understood. The reason we believe dark matter is real is one of the cleanest detective stories in modern science. Back in the 1970s, a brilliant American astronomer named Vera Rubin sat down and asked what looked like a simple question. Why are the outer stars and spiral galaxies moving the way they do? By everything we knew about gravity, stars near the center of a galaxy should orbit faster than stars at the edges, the same way Mercury and Venus orbit our sun faster than Neptune and Uranus. The further out you go, the weaker the gravitational pull should feel, and the slower the object should move, because gravity drops off with distance. Rubin measured star after star, galaxy after galaxy, logging observation after observation, and she found something that simply did not match the rules. The outer stars were not slowing down. They were cruising along almost as fast as the inner ones, as if some unseen hand was pushing them along even when the visible mass alone could not explain it. The only way that could be true was if every one of those galaxies had a great deal of extra invisible mass pulling on those stars. Something massive, widespread, and completely transparent to light. That invisible mass we now call dark matter. And the effect she discovered is now known as the galaxy rotation problem, a name that understates how profoundly her work reshaped cosmology. Her measurements were careful, repeated, and confirmed by other independent teams. The case for dark matter was no longer a clever theoretical idea floating around in journals. It became a stubborn observational fact about the cosmos, one that demanded an answer. Decades later, an entire observatory was named after her, partly to keep pursuing the question she first opened. The Vera C. Rubin Observatory, perched high in the Chilean Andes, carries her name because the next chapter of this mystery is exactly what it was built to handle. It is the sharpest eye we have ever pointed at the deep sky. Now here is the part that sounds almost absurd. Dark matter is estimated to make up roughly 27% of everything that exists in the observable universe. The stars, the planets, the gas, the dust, the galaxies, every photon that has ever hit a detector, every asteroid we have ever photographed, every meteor we have ever tracked, add up to only about 5%. Imagine a cake where the frosting, the decorations, the candles, the sprinkles, the icing, and every ingredient you can name are only 5% of the whole thing. And the rest of the cake is an ingredient you cannot see, smell, or taste. That is what the universe looks like. And yet, after half a century of searching with the most sensitive instruments on Earth, scientists have never directly caught a single dark matter particle. They know it is there. They can map it through the way it bends light from distant background objects, something astronomers call gravitational lensing, where massive invisible structures warp the path of light like a funhouse mirror made of gravity. They can measure its gravitational pull with absurd precision, but what it actually is, what kind of particle, what absurd precision. But what it actually is, what kind of particle, what kind of field, what kind of physics, that is still one of the deepest open questions in all of science. A question that has outlasted entire careers, and that physicists chased through laboratories buried deep underground, far from the noise of cosmic rays that could confuse their detectors. That is why what we are about to talk about matters so much. The galaxy in question sits in a region of the sky near a larger galaxy called NGC 1052, roughly 65 million light-years from Earth. It has a name that sounds like a part number from an old spaceship model, DF9, and it belongs to a category of objects that, until very recently, most people had never even heard of: ultra-diffuse galaxies. The phrase itself was formalized around 2015 by astronomer Peter van Dokkum and his team. They published a paper identifying a huge population of strange, ghostly, spread-out galaxies in a place called the Coma Cluster. a busy little neighborhood of galaxies roughly 330 million light-years away. These objects looked roughly the same size as our Milky Way in terms of the physical space they covered across the sky. But inside, they contained only a tiny fraction of the stars, sometimes hundreds of times fewer stars than a typical galaxy of the same physical size. They were so faint that earlier surveys had simply walked right past them. They were hiding in plain sight, not because they were small, but because their light was so diluted across such a huge patch of sky that it barely registered above the background noise of the cosmos. Picture trying to spot a single candle flame through fog from a mile away, with the flame itself spread out. It's so wide it is barely brighter than the mist around it. That is roughly how faint an ultra-diffuse galaxy looks in a standard telescope image. In the Coma cluster alone, the team cataloged close to 800 of these ghostly structures, a small army of galaxies that nobody had noticed before, simply because nobody had looked with the right kind of eyes. They had been out there the whole time, drifting gently across deep space, quietly existing, and we just could not see them until someone built a sharper tool and asked a different question. That existence alone is strange. Ultra-diffuse galaxies should not be easy to explain. If a galaxy is spread across such a huge area and has so few stars, it is incredibly fragile. The slightest gravitational tug from a passing neighbor, or even the slow internal dynamics of its own sparse matter, should rip it apart like a cloud of smoke in a strong wind. Which is why the leading model for how they survive at all is that they are wrapped in a thick cocoon of dark matter, holding everything loosely together across vast empty spaces like an invisible trampoline stretched across empty space. That makes the new discovery absolutely explosive. DF9 is ultra-diffuse, spread out, faint, ghostly, and almost invisible from Earth. But the way its stars move tells a story that nobody expected to find. In a galaxy with a healthy dark matter halo, stars zip around the center faster than the visible mass alone could ever explain, because there is invisible mass adding to the gravitational pull. In a galaxy without dark matter, the stars should drift more slowly because there is less invisible weight pulling them into circular motion. When astronomers measured the speed of stars inside DF9, they got a number so low that it almost feels like a typo, around 6.5 kilometers per second. That is the spread in their speeds, also known as velocity dispersion. And that number was measured by a powerful spectrograph called the KCWI, the Keck Cosmic Web Imager, mounted on the Keck Observatory high on Mauna Kea in Hawaii. To put that measurement in perspective, if DF9 had a normal amount of dark matter for a galaxy of its physical size, the expected velocity dispersion would be roughly 24 kilometers per second. The actual reading came in at about a quarter of what dark matter would predict, a factor of nearly 4. That is not a small wobble in the data. That is a canyon. That is the difference between the prediction and reality that no reasonable measurement error, no statistical wiggle, no hidden systematic effect could explain away. The team that pulled this off, led by a doctoral student named Michael Kim at Yale University, working under Peter von Dockum, spent more than 10 hours across 2 October nights in 2024 just gathering enough faint photons from DF9's tiny stellar population to lock that number down with statistical confidence. They were specifically looking for a galaxy without dark matter, because the model said one should be sitting exactly where DF9 is sitting. And they found exactly what the model said they would find. This was not a random discovery. It was a prediction made in advance, confirmed by precise measurement. That is the gold standard of evidence in any science, but especially in a field as stubborn and hard to test as dark matter physics, where most observations only whisper hints instead of shouting answers. Now, why did anyone think DF9 would be lacking dark matter in the first place? Because it sits in a straight line, literally in a row, with 2 other galaxies that had already shocked the astronomy community years earlier, DF2 and DF4. DF2 was announced back in 2018. Peter van Dokkum and his colleagues published their findings in the journal Nature and warned the field that the galaxy appeared to contain almost no dark matter. The measurement was so strange that other teams immediately pushed back. Some argued that the distance estimate to the galaxy was wrong, throwing off the calculations. Some argued that measurement uncertainty had been underestimated, that the galaxy was simply further away than the team assumed. The debate dragged on for years, with new papers and counterpapers stacking up on each side. DF4 added fuel to the fire when it was confirmed shortly after, with a similar near-zero dark matter profile, and again the arguments came rolling in. 2 galaxies in the same patch of sky were harder to dismiss as coincidence, but the underlying mechanism was still being picked apart by critics who wanted a more conventional explanation. Then in 2022, Van Dokkum's group published another landmark paper in Nature, pointing out something that quietly shifted the whole conversation. Roughly 10 low-luminosity galaxies in the NGC 1052 field were not scattered randomly across the sky. They sat in a narrow linear alignment, a straight trail, a formation so unlikely to happen by pure chance that it strongly suggested all of them had come from the same origin story. They formed together out of one violent event, rather than being unrelated neighbors that happened to drift into the same region over billions of years. Think of it like splatter paint. When droplets fly off a single moving source, they tend to land in a line tracing the direction of motion. The galaxies in this NGC 1052 trail look like that splatter pattern frozen across 65 million light-years of space. DF2 and DF4 sat right in that trail. Based on the prediction that galaxies sharing the same formation event should share similar properties, the absence of dark matter included, DF9 became a top target for follow-up work. It was exactly where the model pointed. And once the measurement was in, the prediction turned out to be right. The arrow on the map had been drawn, the telescope had been aimed, and the universe had answered. This was the moment the scientific story stopped being an oddity and started becoming a new chapter in how galaxies form. If you have ever wished you could be part of the moment a discovery actually happens, this is the closest thing to that experience you can get on a screen. Drop a comment right now telling me which part of this story hits hardest for you. And make sure you are subscribed, because the next chapter of this is going to land when we least expect it. To understand how galaxies can come into existence without dark matter, you have to picture one of the most visually dramatic events in modern astrophysics: a high-speed collision. Two small galaxies, racing toward each other at enormous velocity, slam together in the dark silence of deep space. Now, what happens during such a collision depends entirely on what the matter in those galaxies is made of. The gas, the dust, the stars, all of that ordinary matter slows down, interacts, gets hot, clumps together, and ends up swirling gently in the wreckage of the crash. But dark matter behaves almost like a ghost. It does not feel friction. It does not slam into ordinary matter in any meaningful way. It sails right through the collision and keeps moving, completely unaffected by the chaos left behind in its wake. The result is a kind of cosmic sorting. In the aftermath of the crash, clumps of ordinary matter that were left behind in the collision zone can cool down, condense, and form brand new small galaxies. But by the time those galaxies come together, the dark matter that used to belong to them has already flown the coop. It is somewhere else in the night, drifting on without them. What forms in the wreckage is a galaxy made entirely of ordinary matter, with essentially no dark matter left inside it. A naked galaxy. A galaxy stripped of its invisible scaffolding, like a building standing without its steel frame. This is what researchers now call the bullet dwarf collision theory, because it is a smaller scale version of something we have already seen at much larger scales. Years ago, astronomers studied a famous pair of galaxy clusters called the bullet cluster that collided long ago in the universe's history. When they mapped the system, they found that the dark matter from both clusters had passed straight through the collision zone, while the hot, ordinary gas had collided and lagged behind in the middle. They mapped this using gravitational lensing, and it produced one of the most direct pieces of evidence ever gathered that dark matter is real and physically distinct from ordinary matter. DF2, DF4, and now DF9 appear to be a smaller scale echo of that same process. Dwarf scale bullet cluster collisions, leaving behind ordinary matter galaxies with no dark matter in them, scattered like seeds along the original path of impact. Here's the beautiful paradox that makes this whole story so elegant. Finding galaxies without dark matter does not weaken the case for dark matter, it strengthens it. Because the explanation for how these galaxies lost their dark matter requires dark matter to behave exactly as the standard model predicts. It has to be real. It has to interact almost not at all with ordinary matter. And it has to pass through collisions like a ghost. The absence of dark matter inside DF9 is, in a strange way, a confirmation of dark matter's nature, a negative space that proves a positive shape the way a footprint proves the foot. Michael Kim said it directly in a statement that accompanied the published paper. The findings, he explained, provide some of the strongest evidence yet that these galaxies form through an extreme and rarely observed process that offers a fresh window into the nature of dark matter itself. A galaxy without dark matter, standing as a testament to dark matter's existence by showing how it can be physically separated under the right conditions, is one of the more elegant paradoxes in all of modern astrophysics. And there are more practical consequences here too. Some researchers, over the years, have proposed an alternative explanation for the original dark matter observations, a framework known as modified Newtonian dynamics, sometimes called EMOND. The basic idea is that instead of dark matter being real invisible mass, the law of gravity itself simply works differently at very low accelerations, behaving in a way that mimics the gravitational effects we usually blame on dark matter. If Mond were correct, in principle there should be no galaxies without dark matter, because the modified gravity effect would always be present no matter where you looked. Finding 3 galaxies that genuinely lack the effects Mond was invented to explain, lined up in a trail consistent with a violent collision origin, is an increasingly difficult anomaly for those frameworks to explain. Not a clean disproof in isolation, but an important challenge that keeps growing with each new data point that gets added to the pile. The alternative explanations are running out of room to maneuver. Now let's bring the story back to the woman whose name is on the observatory. The Vera C. Rubin Observatory began its 10-year legacy survey of space and time, and it is expected to become one of the most powerful tools ever built for finding and cataloging ultra-diffuse galaxies across the universe. Its 3.2 gigapixel camera and 8.4 meter mirror were specifically optimized for exactly the kind of deep, wide-field, ultra-faint imaging that ultra-diffuse galaxies demand. They were built to catch things like DF9 sitting quietly in the dark, spreading almost no light across a huge patch of sky. Think of how a single photograph from a regular camera might miss that faint galaxy entirely. Rubin's camera, in a single exposure, sweeps a patch of sky 9 times, larger than the full moon, with enough depth to pick up objects thousands of times fainter than what the human eye can see. That combination of width and depth is exactly what ultra-diffuse galaxies need in order to finally be seen in the numbers they actually exist. As the observatory's survey accumulates data over its decade-long mission, scientists expect it to flag hundreds or even thousands of new ultra-diffuse galaxy candidates across regions of sky near known galaxy groups and clusters. Some of those candidates, followed up with instruments like KCWI, may turn out to be additional members of entirely new dark matter-deficient trails that nobody has cataloged yet. Each new one would add another clean data point to the case for how and when ordinary matter can be separated from dark matter during violent galactic collisions. That is why this particular moment feels so meaningful. Vera Rubin spent her entire career measuring the gravitational fingerprints of dark matter without ever directly seeing it. She proved, beyond reasonable doubt, that the invisible scaffolding was there. The observatory that now carries her name is being used to find the rare extreme galaxies where dark matter appears to be almost entirely absent. And those naked galaxies, paradoxically, may teach us more about what dark matter actually is than almost any observation pointing directly at its presence. Absence can be just as informative as presence, when the physics behind why something is absent can be predicted in advance and then precisely measured. If this story has shifted anything in your head about how galaxies work, do me a small favor before we close. Tap that like button. Share this video with one person who nerds out about space the way you apparently do, and ring the bell so the next big reveal reaches you the moment it drops. That small action shapes what shows up in feeds for thousands of curious minds who never knew this story was coming. And before we wrap, here's something worth sitting with for a moment. The total mass measured for DF9 from its stellar motion comes out to roughly 100 million times the mass of our Sun. That sounds huge, but compare it to what a normal galaxy of DF9's physical size would weigh if it had a standard dark matter halo. It would weigh roughly 10 billion solar masses. DF9 is missing something like 99% of the mass it ought to have. That is not a small subtraction. That is almost the entire gravitational identity of the galaxy gone missing. And what we expect from dark matter is precisely what is not there. Imagine the universe as a giant balancing scale. On one side, you put the ordinary matter of an ultra-diffuse galaxy. On the other, you expect to put a massive invisible counterweight. For DF9, that counterweight is essentially empty. The scale does not balance, and that anomaly is exactly what we are trying to understand. Star formation inside DF9 is also whisper quiet, almost none. The galaxy does not appear to be actively building new stars in any meaningful way, which is consistent with its lack of a dark matter cocoon. Dark matter halos are thought to help ordinary matter clump together in the first place. Without one, the conditions for fresh star birth may simply not exist. Imagine the moment, decades from now, when astronomers look back at this stretch of research as the moment textbooks started changing. A doctoral student who trusted a model that almost nobody else had tested at that level of precision. A series of galaxies arranged in a straight line across 65 million light-years of space. An invisible substance that nobody has ever touched, weighed, or caught, and yet whose absence in DF9 is pointing us toward an answer we have been chasing since the 1970s. There is something deeply human about that. Science working exactly the way it is supposed to work. A prediction made, a measurement taken, the universe answering back with the kind of clarity that rewards curiosity. Now let's talk about the next chapter, because this story is not finished. The team working on DF9 has publicly discussed plans to measure a fourth and possibly a fifth galaxy along this same trail. The further out from the original collision point those galaxies sit, the fainter they become, which makes the measurements progressively harder. But if even one more galaxy along that line turns out to lack dark matter too, it adds an almost irrefutable piece of evidence, on top of what DF9 just laid down. Other dark matter deficient trails may exist elsewhere. In the sky, some of them might already be hiding in archival data that nobody has reanalyzed yet. Some of them will be freshly discovered by the Rubin Observatory, as it sweeps the southern hemisphere every clear night for the next decade. Either way, DF9 has opened a door that has been waiting for someone to push it, and that is the real takeaway. The universe is not done teaching us. The things we thought we understood at the edges of galaxy behavior, how galaxies form, how invisible matter interacts with ordinary matter, how violent collisions reshuffle the cosmic furniture, all of those understandings just got a brand new constraint laid on top of them. A small, ghostly galaxy called DF9, with stars moving at 6.5 kilometers per second, sitting in a straight line with two others, is teaching us things that no amount of staring at dark matter directly could ever have taught. Vera Rubin opened the door. The observatory carrying her name is helping us see what is on the other side, and the universe, in its quiet way, is rewarding the question with answers we did not expect. If you want to keep following this thread as new, galaxies are measured as the bullet dwarf collision theory is refined, and as the Rubin Observatory starts revealing candidates we have never seen before, hit subscribe now. I will be covering all of it as it happens, because this is one of those rare areas of astronomy where a genuinely major result could land at any time. Tell me in the comments what surprised you most. Was it the fact that a galaxy can exist with almost no dark matter at all? The fact that 3 of them are lined up in a perfect row across 65 million light years? The precisely measured velocity of just 6.5 kilometers per second compared to the 24 that dark matter would have predicted? Or the fact that the very woman this observatory is named after first proved dark matter existed, and now the telescope carrying her name is helping us understand the rare and violent conditions under which dark matter can completely disappear? Drop a comment, like this video, share it with someone who loves this stuff, and I will see you in the very next one.